All right. So now we're going to continue our discussion with what exactly? Right. So we've done black body radiation. So we're going to go over to radiative transfer now. And in particular, we're going to look at some simplified solutions to the transport equation today. Remember, we already, before we started with the black body radiation, we introduced the equation. It was, I remind you, the I nu ds equals eta nu minus alpha nu I nu. Okay? Where these were coefficients which could involve, well, this is emission, and this could involve absorption and scattering. And they're left to be calculated for later in the course. In this chapter, we're going to analyze the behavior of the radiative transfer equation in various contexts, right? And we already looked at the vacuum. In vacuum, of course, eta nu equals alpha nu equals to 0, such that the I nu ds equals to 0, or I nu is a constant. We already knew this from our definition of specific intensity, that it's constant along a beam, as long as there is no interaction with material and no redshift dimming and no frequency shift. We also now looked at the equilibrium radiation case, right? Where we could appeal to Kirchhoff's law, which was I nu equals to alpha nu I nu, but since it's equilibrium, it was just I nu B nu, right? Again, this then resulted in the I nu ds equals to 0, or I nu equals to constant, which in this case was the black body radiation as discussed. But of course, in general, these two extreme solutions are not fulfilled. Yeah? If they were, then yeah, we could stop here. But yeah, they're not always, most often. Often we have situations something like this. We're some observer up here, right? And then we have some object that could be like this sometimes well, sometimes not so well defined surface, as we discussed up here. And then we have perhaps radiation coming in here, but then we could also have material down here, which then could be very opaque if we calculate, if we view it from outside. Perhaps it's very opaque, or it is not so opaque. If we take again the first example, a star, right? The star is very, very opaque. We don't see the inner layers of the star. We see only the small surface layers here. We can say nowadays that the star is very, very hot in the center, where nuclear fusion provides energy. Now, then that energy is transported outwards in large parts of the star dominated by by radiation. So then this transport of radiation is going to go from here to here, and then it's going to be released to us and reach us from the sun here 8 minutes later, because it's free streaming. Okay? Now, in these very opaque, we will see how we can actually treat the radiative transfer as a diffusion process, analogous to matter diffuser or the heat equation. Yeah? Up here, we have the free streaming, the vacuum. Now, in this problematic layer here, we might have to deal with the full transport phenomena of the radiative transfer. Okay? So that's just a little bit of an overview. Huh? So, Another case that we could imagine, of course, is that we have some source here, say it's a very distant star, and then this is then shining on some astrophysical cloud, perhaps a nebula, and then this is then reaching us across here, and then we might be interested, okay, but how is the radiation that enters the nebula then, how is the radiation from the star affected by going through this? Or perhaps we're sitting here such that the only thing that we see, oh, how do I draw this? I should be able to, this is supposed to be an observer, but it's looking in the wrong, yeah, oh, well, anyway. Then there is no background source behind R if we position ourselves here, right? So then perhaps we only see the emission from the nebula itself. And then we might ask ourselves, is the nebula then, or the astrophysical object there, optically thin or thick? And that changes the properties. And we also saw another where we perhaps have a supermassive black hole here. We have an accretion disk around, and then this accretion disk might perhaps be geometrically thin but very optically thick, emitting then here, here, and here, and here. Okay? So these are various forms of objects which we might or might not be interested in. All right. Back then to the equation and how do we actually solve this one? Well, first we're going to do a little bit of a detour again and just mention a little bit on the units. Yeah. The first thing that you can notice is that the extinction coefficient here has to have units of 1 over length. Yeah. So in our lovely CGS units, 1 over centimeters. Hopefully that's clear because this is the ID I over S, which is a length, yeah? And here you have the I, right? But the emission coefficient doesn't actually have those units. So to see what that has, it's units of the intensity, the S, right? So if we appeal back to our definition of the specific intensity, right, you remember that it was the energy in the frequency band time per unit time per unit area per unit solid angle. Okay? Oh my God. It's been a long day. Okay? And then, of course, if we take this per unit length, we get a volume down here. So we get something which is the energy per unit volume and then per unit time, frequency, solid angle. So you can see the emission coefficient in this way as the energy added to the beam of radiation per unit volume, per unit solid angle, per unit frequency, per unit time. So again, going back to our basic definitions, right? So this is a volume energy addition to the beam. This has different units. That's per length. All right. Now we're going to try to solve it. Yes, we're actually going to solve it. Well, soon at least. We're going to work with it a little bit more. Because what we can do here, okay, we're going to divide through by the extinction coefficient. Then we get something which is like this, right? equals eta nu divided by alpha nu minus I nu. And from this, we can define two very useful quantities. I will just write up here this as d tau nu, S nu, minus I nu, such that you can see that d tau nu equals alpha nu ds, or if we just integrate this, then tau nu is the integral alpha nu ds. This is the optical depth that I was referring to already before the break in the discussion. It's just a measure of the extinction integrated along the beam. So a measure of the total extinction, the optical depth. Now the other quantities here, it's just defined as the ratio between the emission and extinction coefficient, and it is called the source function. Okay? Hopefully, at the end of today, it will be clear why. Yes? The question was whether this was an S, and this is indeed an S. I apologize, my handwriting is poor today. This, though, is actually not an S. This is an integral. Aha. Huh? Now, the reason I write so poorly is, of course, that we need to be aware of this from the context, and it needs to be clear. I wish it were that reason. All right. Let's now say we're going to start with the example of there is no energy, there's no intensity added to the beam. So we're going to set eta nu to 0, and then we're just going to solve this one. The I nu ds, but I'm going to reformulate it in the tau nu directly, minus I nu. Okay? Well, that's neat. That's a differential equation that even I know how to solve. Yeah? Like this, like so. And then we can solve it, getting out that I nu, let's call it out, is I nu in e to the minus tau nu out minus tau nu in. Okay. So that was simple enough. This is the exponential law of light in the case of pure absorption or pure extinction. Yeah? So you can imagine, for example, you have light reaching us, yeah, from the sun. Here is our atmosphere. We're standing here looking up. Yeah? And then the light here is hitting our atmosphere. And then it's going to travel through our atmosphere and then hit Earth if we see it. Yeah? But then, of course, since it's traveling through the atmosphere has a lot of particles, can get absorbed, or extinct, or scattered. Yeah? And if we make the assumption now, well, for the optical wavelengths that the sun emits, we're not going to have so much energy added to the beam. It's just going to be absorbed. Then you can calculate the amount of that absorption by just saying, okay, the stuff in our atmosphere, and this is the stuff that reach us, right? So what reaches us is the stuff that enters our atmosphere, e to the minus, and then tau nu is just the optical depth of, in this case, our atmosphere, where I've just set that, okay, tau nu in equals to 0. Definition we can make. So as we know, for example, light in the ultraviolet doesn't reach us much, yeah, unless we have problems with the scattering absorption molecules. And then the absorption is efficient, the optical depth becomes high, which in this case means that if we think about what the optical depth was, it's the integral of alpha nu ds. If we assume that this is spatially constant, that's just an approximation now, this would just be alpha nu L, right? Where L then is the length of the atmosphere, or the height in this case, sorry for saying length, of the atmosphere. And then if this is high, at a specific wavelength, then we won't see any light from that. If it is low in another wavelength, we will see it. This is what happened in optical lights. Now, I should say that for an atmosphere like the Earth, this is a little bit complicated by the fact that it's not pure absorption that dominates, but it's actually a scattering effect, and we will come later to that. The ideas there. Another thing that we can think about when we have this exponential decay is that, okay, we have some sort of object that travels to us. Now this is not our sun, this is a star in our own galaxy or something like that. And then it's going through a lot of interstellar medium, or even intergalactic medium if we look at a galaxy far, far away. And that intergalactic medium then, or interstellar medium, can of course absorb some of the material emitted from the source that we're interested to analyze. And then that also gets extinct by this law. And in the absence that something is re-emitted into it, then it again follows this exponential. This is then called interstellar extinction or intergalactic extinction, etc., etc. It is very often by dust particles that can provide this, and dust grains. In a combination of absorption and scattering in that case, normally. Now, perhaps one very famous example of, so to say, the context where this is very important is when we analyze stars close to our own Milky Way galactic center. Yeah? So remember that there was a Nobel Prize awarded to those who analyzed the motions of the stars close to our galactic center, and by analyzing those motions, they derived, or they obtained estimates of the central mass that must exist there, and came to the conclusion that this must be a supermassive black hole, or a compact object at least. Yeah? Now, the trick with those observations is that you can't do them in our normal telescopes tuned to be efficient in the optical, because there the intervening opacity, like here, is so high that there is barely any light reaching us. We even saw an image of this in the first class, if you go back and look in chapter 1. Right? So they had to go to different wavelengths, in this case to the infrared and even radio, in order to get less intervening absorption material, because the extinction coefficient or the absorption scattering coefficient at those wavelengths is much less. So then you see then it's more transparent, and you can actually see the motions of the star and then derive the constraints. So that's a direct example of that. But all right. Under most circumstances, though, we're not just going to deal with the absorption, but eta nu is also not, the emission is not going to be zero. So then we have to solve the full equation. And again, I'm going to write it on this form, okay? S nu minus I nu. Okay. So how do we solve this? Well, this is in this form, the radiative transfer equation is a linear ODE, ordinary differential equation. So we're going to look in our Calculus A book and see how we can do that. Actually, we can do it with an integrating factor, which is E tau nu. Okay? So let's introduce that integrating factor into this. Tau nu, S nu minus I nu. If we look at the, if we pull over this to this side, we get this term, right? The tau nu e to the tau nu plus I nu. It must be an E. Yes, I missed that. Somebody should have said something. E to the tau nu. And we can see that this is indeed then the integral, no, the derivative of e to the tau nu. I nu, but just the chain rule. So then we have the form tau nu, I nu equals, I should have something on the other side as well. Tau nu, S nu. Okay, so we integrate this again between two positions, yeah, in, say, a slab here with some sort of I nu in, with some sort of I nu out, right? And some sort of tau nu in, which we will later set to 0, and some sort of tau nu out. And then we will have I nu out, e to the tau nu out minus I nu in, e to the tau nu in equals, well, we're going to go directly to what we call a homogeneous slab solution now in electron notes. So what we're going to assume in order to solve this and get a closed expression for now is to say that, okay, the source function inside this material is constant. Okay? If the source function there is constant and not the function of the position in the slab, then yeah, okay, this is just S nu e to the minus tau nu out minus e to the minus tau nu in. All right. And we can say, just define that the incoming optical depth is just 0, such that we have E out. And then we can just call this tau nu, so we don't have so tricky notation. Yeah? This is just I nu in then, and this is just going to be S nu e to the tau nu minus 1. Okay, did we do many algebraic mistakes on our way there? We will soon see, I guess. I haven't heard anything, so I hope not then. All right, so this is then often put in this form. E nu out equals to, we pull over to the other side, E nu in, right? And then we add the source function. This one will have to move over. So this becomes 1 minus then e to the minus tau nu. And this is a solution that if you take some courses in astronomy and astrophysics, you will likely be exposed to more. It is the solution of the radiative transfer equation through a homogeneous slab. So okay, what is going on here in this expression? Well, of course, first we need to do some sanity checks, right? Can we recover the previous stuff? Well, there is a term missing first. Yeah? Which term is missing? Which term is missing? E to the minus tau nu. Remember, I had a e to the tau nu on this side. This one was multiplied. So, of course, when I divide through that, it becomes minus there. That's why this had to turn. Yeah? So, but I forgot it there. Oops. It's there now. So now we're fine. All right. First, the vacuum solution. The vacuum solution in this context, we can realize by just setting tau nu strict to 0, right? Well, tau nu strict to 0, this becomes 1. So this is it, and this becomes 1 minus 1. So that's 0. Huh? So then we have I nu out equals to I nu in. So that's, again, the thing that we have seen many times now. Good. The pure absorption solution. Well, then, that was eta nu equals to 0, right? Eta nu equals to 0 means that S nu, eta nu alpha nu equals to 0. We set this to 0. We get I nu out equals to I nu in, e to the minus tau nu. That we also saw, so we check that box as well. But in general, of course, the source function emission coefficient is not 0. And then we have this. So we're going to look at some cases here now. Let's first say that, okay, now I have this optically thick medium that I have referred to several times today now. Tau nu then is much, much greater than 1. That is what it means to be optically thick, as we alluded to already. And what happens then? Well, if tau nu is much, much greater than 1, it's not fun to be up against an exponential, as we keep reminding ourselves. So this will just go away. This will just go away. We're left with just this term. Then the outgoing intensity is just the source function. Hence, the name source function. So what does this mean? Well, if we have our slab now, okay, and we have something, I nu, that comes in on this direction. We're sitting here, and we're interested in the I nu out here, right? But then this one is so optically thick, then, of course, analogous to what I said with the building, if it's foggy, I don't see the background building. The background building here being our source. But everything is absorbed by the intervening material, and the only thing I see then is the fog. The fog, in this case, would be whatever comes out there, which in this case is set by whatever the source function is. So in an optically thick material, you don't see the background source, but only the source, the emission material there. And this should be hopefully intuitively clear to you, but this is how it is reflected in the solution of the homogeneous slab radiative transfer equation. Now I should say, and we will come to this on Friday, that in the more general case, of course, the source function cannot be taken as a constant throughout the whole medium. It's actually varying. And then we are left with an integral equation to solve here, as we will see. And then in various, we can use various approximations for the source function to still perhaps get out an analytic solution, or we will simply have to do it numerically. We will look at specifically one famous analytic example of this called the Eddington-Barbier approximation. used classically to explain a phenomena like limb darkening. All right, where were we? Yes, now we're going to see the other case, and that is that, okay, perhaps we have some optical depth, yeah, but it's very small. So it's not zero, it's not vacuum, but it's much, much smaller than 1. This is what we call optically thin. We do have some emission, but it's very thin. Yeah? Then again, we come back to the same Taylor expansion as before, right? Now, we're going to use this Taylor expansion for this limit, as before. And then we're going to look at that equation, and we're going to see I nu out in this case now is going to be I nu in 1 minus tau nu, and then plus S nu tau nu. The ones vanish, yes. And it's convenient to write this on this form, I think. Minus I nu. Okay. So what can we say about this situation here? Right? Well, first, this is I nu in. You can see, okay, what if we had this cloud situation that we discussed before? We were sitting here, and we were just interested in emission from the cloud itself. Yeah? We didn't have any background source, right? Well, then I nu is I nu in is 0, right? That we can agree on, I hope. And what will we see from such a situation? Well, I nu out is going to be approximately then the source function times tau nu, okay? Now, what is tau nu in this sense? Tau nu is the integral over the slab now. This is not S. Alpha nu S, okay? And we're going to get some insight, we're again going to assume that this is constant throughout the slab, right? The homogeneous slab. And then we can just say that this is alpha nu times L, where L now is the length scale of the slab, right? But the source function, of course, is eta nu divided by alpha nu. So we can see that this is just then I nu out. It's just the emission coefficient times the length of the slab, which also should be sort of intuitively clear. We had no background source. There's nothing to be extinct. The only thing we see is like the energy per unit volume being added to the beam in our direction from the cloud itself. And then, of course, we have to multiply this because this is defined that way times the length of the slab. Yes. Now, what if we have a background source? Okay. We have a background source, which is some sort of I nu in. Then we can say that, okay, we can just look at the equation and say that I nu out will be greater than I nu in if S nu is greater than I nu in. Similarly, I nu out will be smaller than I nu in if S nu is smaller than I nu in. And if they're equal, well, then, you know, as much is added as is subtracted, so to speak. So then we just see the background source, right? Now, in application 8.3, we will use and extend this simple way of thinking whether the intensity that reaches us is higher than the background source or lower than the background source to explain various objects which are characterized by emission lines and absorption lines. I can already now allude to the fact that, okay, if the source here is often under at least local thermodynamic equilibrium situations, the Planck function, right? And if you think about the background source also some sort of Planck function emitter, right? Then you can immediately see, okay, but if the temperature here in the intervening stuff is hotter than the background, then we will get more emission out. An emission line, if we think about the line case. Vice versa, if it is cooler, an absorption line, right? An emission line is often what we see from nebula. Absorption lines is often what we see from stars. Why is that? Well, in this, using this framework, it is because the temperature in the emitting layer is cooler than the background source. Think about the background source as the deep layers of the star. And we know that stars are hotter in their cores than at their surface. All right. Okay. We will extend on these ideas and the radiative transfer equation further during next class. Thanks.